Welcome. At this point, I am going on the honor system that you have already read the fractions review paper that I put up for you, and that you have had a chance to at least try. One minor note before we go too much further, I noticed that in the actual assignment I gave you, the two fractions were 1/2 and 3/4. That should be fine. We have a bit of a difficulty, however, in that the work through example that I have, I used 1/5 and 2/3. Every semester I alternate between those two fraction pairs, and I suppose I must have thought that I was in the off cycle here. What you should find is you should find that the actions and the objects are identical. The only difference is what numbers specifically. So instead of sharing with 2 and taking 1, you'll share with 5 and take 1 in the example. To make it fair, however, I will post a second example where I work through using the 1/2 and I believe it's 1/2 and 3/4 that I gave you to work on. So, I still recommend that you go through the first example. And in fact, I'm going to post that first. Then I'll wait a day or so before I post the worked through example for 1/2 and 3/4. As you read through the fractions paper, one of the things that I'm hoping that you realize is that even though many students do have difficulties in dealing with fractions, often those difficulties are due more to the lack of an accurate model. And in particular, when they don't have a model, they fall back on understandings and procedures that they might remember, they might not remember. It's kind of funny, the example I gave you where they have 1/2 plus 3/5 is equal to 4/7, if you remember that. What's happening there is they're adding the numerators, they're adding the denominators, and they think that that's correct because they seem to remember a rule somewhere where you did something across the top and you did something across the bottom. Multiplication, isn't it? And so they're confusing this multiplication rule for the addition rule. And what's really sad about it is that if you ask the students, and I've done this, ask the students, they will tell you that their teacher taught them to do it that way. Now, I know that the teacher didn't, but in the student's mind, they truly believe that they were taught this incorrect rule. And this is very typical of students when they are memorizing rules rather than understanding. They will honestly believe that their rules, as they memorized it, are correct, and that's what they were taught, even though we know that that's not the case. At any rate, it's a real problem. And so when we think about it, part of the reason it's a problem is unless there's some way of making sense of it, there's nothing else they have to fall back on. I remember asking a student, does this make sense to you? And they came back saying, well, no, but it makes as much sense as anything else I've ever done in math. Again, not a good scene. So to combat this, the referent, and by referent, I mean the physical object or the sketch or the manipulative, whatever we're acting upon, the referent we use to model fractions, and that will then generate our operations. Remember, comparison, addition, subtraction, multiplication, division. That model has to be easily understood. And if it's not easily understood by the student, if it's not generalizable by the student, it doesn't matter how well it reflects the math. It has to be something that is understandable to the student, that is accurate as well. And so when we think about what's important here, we have to be able to represent and what the representation means. We have to be able to compare. We have to be able to model addition, subtraction, multiplication, division. And we also have to understand the link between these models and the procedures. I am hoping that you see the links between numerical fluency as we developed it in whole numbers and also numerical fluency as we need to develop it in every other type of number, whether that type of number is fraction, whether it's decimal, whether it is common fraction, whether it is polynomial. We have to do the same thing. And so when we look at this, how do we go about doing it? Well, the first thing we have to do is find a common set of experiences. In the handout I had you read, I suggested that you fall back on the notion of sharing. Most children have shared. They may not want to admit it all the time, but they understand what it means to share. They also know what it means to share fairly. It's not going to be fair if we're sharing 4 things and I get 3 of them and I only give you 1. All right, we have to make sure that it's a fair share. And once this is done, we have pretty much everything we need except for a little bit of symbolism to talk about denominator. And so as we indicated in the handout, if we have the bar with a 2 underneath, we'd read that share with 2. We had share with 5, so on. And so sharing becomes our action that we perform. The object that we perform it upon becomes the manipulative or the sketch or the referent, if you will, for the modeling process that we'll use for grounding the mathematical sharing. And so, in other words, the denominator and division in general will be pinned to these concrete actions that are based in turn on earlier experiences like sharing. Now, in looking at some of your early work, I couldn't help but notice that a lot of you have had experience with pizzas, it looks like, because I saw some circle models. I didn't make a big thing about it, but when you saw my papers, you noticed that everything was a square model. And I want to spend some time right now as we think about this more carefully in terms of why is it that the square model, which I've always called the magic cake, has a better representation than the circle or pie model. I'm willing to bet most of you have had more experience with pies than you have with cakes at this point, at least in terms of fractions. And it's rather unfortunate because the importance of reference selection is quite obvious when you consider why we selected square as the geometric object to use to act upon. So let's take a look for a second now about how we'd go about developing fraction ideas using each. What it would look like if we used a unit square, which I'll call a cake, or a unit circle, which we'll call the pizza model to go along with what students might have experienced with. So these are the 2 objects that we might choose. We can select a pizza or we can select a cake. And let me go ahead and share my screen with you on this, and let's take a look and see what that might look like. So in looking at this, what we see is that we have a cake and we have a pizza over here. We are going to act upon those, and the action we perform is share with 3. So as we do that, we can show that action by cutting it into 3 approximately equal parts, and then we do a little bit of let's pretend, and we will pretend then that those are the exact same size, exact same shape. After all, I'm not going to cheat you, right? So having done that, then what we will do is we'll play this out to see what differences it makes when we go beyond just simple sharing, because they're both equally good so far. By the way, when you think about actions you can perform upon cake and pizza, cutting is one that you can perform upon both. And so just as we used share with to identify the notion of creating equal sizes, we can use cutting as an action that has a very concrete component to it to go along with this more abstracted notion. In this case, when we talk about sharing an object, cake or pizza, we're going to be cutting it into an equal number of parts. So we have both the appropriate actions and the objects upon which to model these actions so that fractions can emerge equally well. At this point, there is no real difference between the two models. And in fact, this is probably as far as most people push it, unfortunately. Now, I have to tell you at this point, a little bit of let's pretend is helpful. Whether we're talking about a cake drawn with great precision using a graphics program or one sketched in haste on a student's paper, we have to pretend that they all represent the same underlying cake. Some middle school students have gone so far as to laughingly refer to these as magic cakes due to the let's pretend consideration, and I guess that's what I'm drawing upon when I call them the magic cake. Now, when we consider what understandings now can emerge, when the action share with 3 is applied to both objects, whether a cake or whether we have a pizza, if we take a look at what that looks like, we see something that looks like this. All right, so over here we have our cake, we have our pizza. Again, we have the action, share with 3, like we talked about. They don't look the same, but the understanding at least can be the same. And what we will want to be able to do is we'll want to be able to perform enough of these actions so that the students are accurately able to share with any instruction, whether you use a cake or a pizza at this point, and they need to be able to do it quickly. There's 2 modeling considerations that you have to develop at this time. And we hinted at this in the handout, but I want to make it very explicit. First among these is that each cake or pizza, whether drawn on the board or sketched on the paper, represents the same idealized object and is exactly the same size and shape. We think about it, and admittedly, this is an ideal, and even mathematicians have to make a little bit of let's pretend, I guess, when they pretend every unit square is exactly the same size. Well, that's what we're doing. That's what we're asking our students to do. I have found, oddly enough, that the more time that a teacher spends trying to make everything look perfect, the less the students understand the concept you're trying to develop. They get so hung up on wanting to make everything look perfect, they forget that, well, let's just pretend it's all the same size and same shape. Much easier to play let's pretend than to waste a lot of classroom time trying to draw perfection, because you won't be able to do it anyway. You'll get close, but you won't be able to do it anyway. The second modeling consideration you have to concern yourself with is developing the notion that I wouldn't cheat you, Pa. Remember Pa and Ma Kettle? I wouldn't cheat you. And so even though each share might not look perfect, they really are all the same size. Again, as we develop these 2 notions, what I find is that young children have no problem doing this. It tends to be the teachers who have a hard time with it, and they spend a lot of time wanting to make something look perfect when they'd be better off just relying on the sketch. Now, at this point in the modeling process, whether we use the cake or the pizza, what we've done is we've developed a robust understanding of share with. Now, in mathematical terms, share with refers to the denominator portion of the fraction symbol. And so as we develop the conceptual background for the numerator or the take portion, we address ourselves in terms of expanding the way we would read. So if we looked at the symbol for 1/2, we literally would learn to read that not so much as 1/2, but as share with 2, and then take one of the 2 shares. Now, if we think about what that might look like in terms of the fraction cakes, we can model that and we can take a look at it. And when we do, this is what we see. We see that, again, it's not as different as what we might have expected. You see over here, we have our cake, we have our pizza. What is the action that we're performing? Well, the action that we're performing is, as we said, share with 2, take one of the 2 shares. So let's see what that looks like. On the cake, we share it with 2, so we pretend to cut it into 2 parts, and we take or shade in one of those 2 parts. We do the same thing with the pizza. And again, so far, so good, isn't it? We're not seeing anything at this point that would necessarily make one of these models stand out above the other. So as we look at this, so far at least, we're thinking, well, okay, one model is the same as the other. How come Doc made such a big deal about going with the rectangle, going with the square? It starts to show up in comparison, which is our next operation, because what we've done so far is we have represented. And when we start operating on number, thinking back to our numerical fluency model, remember we represent, then we represent again, and then we ask the question, which is larger. And so once we hit that point, I think you'll see where one model begins to have a little bit more impact in terms of being understandable than the other. Now, when we go back to this, just remember that we are not viewing these symbols now as abstracted. 1/2 is actually telling us to do something. It's telling us to share with 2 and then take one of the 2 shares. That's very concrete. That's not just saying this looks like 1/2 because it looks like it. We could get there with Van Healy, but this is more important. This is saying that we're actually doing something. We're taking this, we're creating 2 equal parts. So it's a partitioning or a division problem, if you want to think about it that way. And then we're taking one of those 2 parts. Now, if this is as far as you go, and you're in 3rd grade, you're actually in pretty good shape, because you now have all the understandings you need to use a model and to identify any fraction symbol, which is pretty important on the STAR test, isn't it? So being able to represent fractions just this much will place students in a strong conceptual position to understand other models when they see them. Now, from a purely representative fashion, I just want to make this point. At this point, cake and pizza is performing equally well. So as long as we're thinking of different models here, let's see what happens if we want to compare 2 fractions. And I'm picking something that's different from any of the models that I've had you do. That I'm going to use 1/4 and 2/3. So the first step in this will be to represent the 2 fractions to be compared. And again, we've built a pretty good case, I think, that both of these can be modeled equally well with either cake or pizza. And so what I'm going to do then is I'm going to take a look now at what 1/4 and what 2/3 would look like if we model it in both cake and pizza terms. So all right, so now as we take a look at this, we've represented 1/4 and 2/3 with our cake model. 1/4 meaning to create 4 equal parts and then take one of the 4. So share with 4 and then take 1. 2/3 would be to share with 3 and take 2. So you notice we're sharing with 3 and we're taking 2. And we're cutting the cake in horizontal and then in vertical. That's an old baker's trick to make sure that you can cut the cake equally, because in a square, we can share in one direction, we can share in another direction. And because it's the symmetry of the square, we know that the pieces are going to be the same size. Turns out that's pretty important. We can't say that about the pizza. The pizza model, though, again, we can continue doing it. We can share with 4, so we create 4 parts. We take one of the 4 parts. We can share with 3, and we can take 2 of the 3 parts. And since all we've done so far is represent, from a representation perspective, we're okay so far. But when we look at the next section here, what is it that we need to do when we go to comparison? Well, we have to make the pieces the same size. And as we look over here, we see that that starts looking a little bit more complicated, doesn't it? So let's see what is happening at this point. It might have been tempting to have made the comparison just based on visual inspection, but you really can't do that. In order for a comparison to be valid, you have to show that each section has to be compared has the same area. And the simplest way to do this is to redraw each representation so that both sharing instructions can be performed on it. And so to go back to our picture here, you'll notice that what we did is for the cake model, we have taken it so that the instruction share with 4, which is already in place, can now also be done with share with 3. So both share with 4 and share with 3 is being able to be done simultaneously. Over here, you notice we had already shared with 3, so we cut it the other direction to show that we have also shared it with 4. So depending on how we look at this, we can either describe it as sharing with 4 or sharing with 3. And because we're dealing with a unit cake, and because each of those shares represent the same amount, and I wouldn't cheat you, Pa, that means each of those little pieces represent the same amount of cake. So we can consider those pieces as being the same size. It turns out that's extremely important. You'll also see over here that when we look at it, it's not nearly as much fun when we start thinking about our pizza. And here's where the pizza starts fading as being a good model, because in order to share with 4 and then also to share with 3, we have to take each of these 1/4 pieces and share each of them with 3 parts. And likewise, we have to take each of these 1/3 pieces and share each of them with 4 parts. Now, I am going to tell you right now, for most young people, they are definitely going to find it much, much easier to take a look at a cake and just cut it in one direction vertically, another direction horizontally, then they're going to find if they have to go over and divide up this circle and then divide up each of the pieces within the circle, clearly that's more difficult. And it's at this point where you should start seeing where this cake model really has a lot more to say for it. Now, in the picture you saw, you'll notice that each of the representations were shared with both 4 and 3, and that represents 12 equal area pieces. A simple counting would then be able to finish this comparison with the result that share with 3 and take 2 is larger than share with 4 and take 1. And it's going to be the case whether you use a cake or a pizza. And, you know, I think you've got a good case going at this point why the cake is a little bit easier. Let's just show, however, though, for completeness sake, that it's still possible that you would be able to do the same thing from a record of action perspective if we looked at what this might look like. And I counted up the number of pieces. And you should notice this is starting to look more and more like our template that you've taken a look at. If I count the number of pieces I have here in 1/4, if I share with 1/4, I'm basically creating 4 equal parts. I'm taking one of them. I'm building the comparative form by cutting it in the opposite direction. I get 3 pieces. 3 times 1 is 3. There's my 3, and there's my 1. You'll notice that the share with from the opposite fraction tells me how many additional pieces I have to cut each of these shares into. So when I'm thinking of 2/3, you'll notice that I have these 2 thirds already. I have the 2, and I'm going to be cutting each of them into 4 equal parts so that I can share both of these with the same numbers, 4 and 3. So 4 times 2 gives me my 8. Because we're used to thinking about the area model for multiplication, the multiplication here is very simple to visualize, and it ties back into earlier experiences with whole numbers that the students should be familiar with. On the pizza side of the world, it's a little bit more difficult to show that 4 times 2 gives you 8 and why that should be the case, because the model for multiplication isn't as obvious in this case, and it frankly doesn't buy as much for the students in terms of predictive power. So if you wanted to, I guess, what we could do is we could develop a record of action for both pizza and cake, and you could have your own equivalent template, if you will, that would look like this. Here's our generalized template for the cake model. Here would be a generalized template for the pizza model. But what I hope that you're seeing is that I really, really do not think it's a good idea for us to be using this model. This model over here does not buy us nearly as much. This model over here is the one that we're going to be using because it allows us to cut both horizontally and vertically, and that ability gives us a significant heads up in terms of ease of use when we start applying that model for our students. Again, I believe you can see the difference between our two references now quite clear. The cake model, due to the ease with which it can be divided both horizontally and vertically, is ideally suited to create equal divisions. In this case of 4, 3, and 4 times 3. While this task can also be accomplished using the pizza model, it was much more tedious, and the resulting record of action was confusing at best. Now, when we push this forward, I just wanted to share with you that we can generalize this to a general case. We can generalize the case of comparing share with B and take A, and share with D and take C. And that's about as general as you're going to get, isn't it? So for any old numbers at all right, A, B, C, and D, what we can do is we can imagine, if we will, carrying that out on our template. So if we take a look at our template and we see what it is that we could be doing with it, over here we have share with B. So how did we do that? Well, we're going to cut everything up into B equal parts horizontally. And I'm showing that by showing that from here to here, that represents B parts. Then we are going to take A of those B parts. And I'm purposely making this look a little bit vague just so that you realize it's any number at all. It's not just 1/2 and 2/3 and 3/4. It could be any number A and B whatsoever. So when we read share with B, take A, that means we just cut it up into B parts, and then we take A of those B parts. When we take D, share with D and take C, that means vertically we're going to cut it into D parts. See how that? There's my D parts going up and down. And then we're going to shade in C of them. All right, so again, it sounds a little bit of alphabet soup here, but it is making hopefully some sense. Let's show you what it is that this looks like now when we draw it out. In particular, what we'll see is we will see that as we go across here, see there's my A parts. And how many pieces is it broken up into up and down now? Well, it's D. So how big is this rectangle? Well, because we know our area model, we know that this rectangle from here to here and here to here is something that is A in one direction. See that? There's my A. and it is D in the other direction. When we're comparing that, we ask ourselves, well, how big is this rectangle? And I think you can see the answer, can't you? When we look at that particular rectangle, we see that it is B in one direction by C in the other direction. And so there's my pieces going across. I have B of them, and there's my, C pieces going up and down. Sorry, I got a little bit complex there. I didn't mean for that to look as ugly as it did. Maybe I can erase it a little bit. There we go. That's a little bit better. So when we say how big is each piece now, what we've got is we've got a really nice way of saying it. So when it's time for a generalized comparison, we have a nice way of seeing how large it is. Our rectangle over here is B in one direction and C in the other direction. So there's our rectangle. When we compare that with our rectangle on the other side, what we have is we say, well, how big is it? Well, remember, it was A in one direction by D in the other direction. Well, there's where I'm finding my D. There's where I'm finding my A. And that's my product. Now that we've seen how this works in a totally abstract sense, hopefully you'll be able to apply this to any fractions whatsoever of the form share with B, take A, and share with D, take C. So I'm feeling fairly confident at this point that you see this is a generalizable model, and it's something that will always work for you. So when we think about that, once you understand the concepts, you'll notice how quickly we get beyond numerical fluency into something that now we can show graphically, even from a Van Healy perspective of what does it look like, that still ties into some formal reasoning and proof along the lines of the division by 9 problem. I will be the first to admit that these models do take some practice. I would encourage you to watch these videos, to reread the instructions, to go through the work-throughs until they are second nature for you. I think what you will find is that it will be harder for you as an adult to learn how to use these than it will be when you start applying them in your own classroom with your own students.